Okay, welcome to lecture 11. We're repeating this for the students that were in quarantine. Um, Hopefully, we'll get everything covered. So, again, lab this week, Thursday, October 1st. We'll meet at 1 p.m. at the digester and we'll continue our discussion on preserved feedstuffs. I think that's what we're doing. No, we may be meeting the sale barn depending on the weather. We'll meet up there somewhere 4 o'clock on Thursday for our lab. What do we got? First exam October 1st. The other exams are scheduled there. Again, we're going to have to be COVID flexible as students come in and out of quarantine, depending on the dorms, how we get this done, when we get this done, how much longer we're on campus. So we introduced the concept last time of breaking down the feed in a feedstuff and introduced the concept that it may not all be available to the animal. So when we think about partitioning energy in a feed, the first concept we have to introduce is the gross energy of a feed. So if we take the feed and we burn it completely to CO2 and water, there's a certain amount of heat that's released. That is equivalent to the gross energy in that feed. All the energy that was captured from sunlight will be released. So to measure the total energy within a feed, we do something that's called bomb calorimetry. Bomb calorimetry is a small steel container. We put the feed sample in there. We cover it with a lid that's got electrodes on it. We submerge that whole thing in water and we run electricity through that feed stuff and we burn everything to CO2 and water. And what it does is heats up the metal. That metal transfers the heat to the water, and we have a measurement of the heat in the water. We can measure that. We know how much water's there, how many degrees it goes up. That is an indication of how many calories were in that feed sample. So that's the total amount of energy. Not all of that is available to the animal. The next step down is the digestible energy. The feed goes in the mouth of the animal. As it passes through the digestive tract, energy is extracted from that feed stuff. What leaves through the anus at the other end still has energy in it. We can think about the pioneers going across the plains. They used buffalo chips as a source of fuel, so there is energy there. So the difference between what went into gross energy and we subtract the fecal energy, that difference is called digestible energy. This is the energy that's potentially available to the animal, and we know that not all of that will be available. We lose efficiency at each step. So digestible energy is very similar to an old concept called TDN. So TDN stands for total digestible nutrients, and it was measured on a percentage basis with a feed. 60% TDN might be typical for a forage, 50-60%. Corn might be 80 to 90% TDN. TDN is the sum of the percent of digestible crude protein, the percent of digestible non-structural carbohydrates, plus the percentage of digestible NDF, and then percent of digestible fat times 2.25, and we'll explain why that is in a bit. There's a photo that will be posted showing the chalk related to this discussion. I drew the TDN equation on the board. Partitioning the energy in a feed. The next step is metabolizable energy. We start with digestible energy and we record the energy associated with energy lost while it's digested. It goes through processes that are not available to the animal. So this is urinary losses, specifically the energy in urea that is excreted from the body. Energy is a fairly energy dense molecule, but none of that energy is available to the animal. The ammonia in there, and then the gases. So we talk about fermentation, gases are produced. One of those gases is produced in about a third, maybe 20%, 10%, but methane. It has a lot of energy in it. That energy in the methane is not available to the animal. So we've got digestible energy minus urinary and gases energy leaves us with metabolizable energy. So the next step is partitioning the energy in a feed. We're going to take our metabolizable energy and we're going to subtract heat increment, the heat lost in the conversion, and we're going to be left with net energy. That heat increment can be good or bad depending on what state we're in or where that heat might be used in the body. If it's cold outside, that heat can be used to generate or maintain the body temperature. If it's hot outside, maybe that's more heat that we got to get rid of, and that's not as useful. So heat increment, the loss of heat associated with the conversion of Me to Ne can be good or bad. So the conversion of Me to Ne varies in efficiency, the relative capture of that energy. So net energy maintenance, NEM, is with the lowercase m there, is a rather efficient capture of that metabolizable energy, and that has to do with warm-blooded animals can use that heat to help maintain their bodies. Net energy gain, NEG, capital N, capital E, lowercase g, is not as efficient. That energy really doesn't help lay down skeleton, doesn't help lay down fat, doesn't help lay down muscle tissue. That's just excess loss. So the efficiency of transfer from metabolizable energy to net energy is not as efficient. Lactation energy, NEL, we'll be using this phrase a lot, getting to balancing rations. NEL is net energy lactation, and that's about as efficient of a capture of the metabolizable energy as our maintenance. Lactation is a fairly efficient function. So if we take that discussion, what we've done so far, we can see that this is a schematic of what we've talked about. We start with the gross energy of the feed. We're going to lose a certain amount in the feces. What's left is the digestible energy. We're going to lose the energy in urine and gases, specifically urea and methane. And then we're going to have metabolizable energy. We're going to have some losses related to heat. That's going to leave us net energy, which we can use for maintenance or production. We can look at it another way. We have a bar chart here with all the calories that are in a feedstuff and where these calories might end up. They're going to end up in the feces, the urine, heat increment. So feces, urine, heat increment, maintenance, or the net energy gain, net energy for eggs. So when we look at this whole bar here, the whole bar is gross energy. If we lose the fecal energy, what's left is the digestible energy that includes those 4 sections. We drop the urinary, and we're going to assume there's not a lot of gas energy associated with the cows. They don't, or not hens. We got a laying hen down here. They don't burp all that much. What's left, heat increment maintenance, eggs and tissue is metabolizable. The maintenance egg and tissue is our net energy for production and maintenance. So where have we seen something like this before? So I drew up on the board. We can think about this very similarly to the money in our paycheck. So we have a gross income, and then what we get take home, our take home pay is our net income. So you might think that we've got 3 losses here along the way that might be equal to federal taxes, state taxes, and Social Security. And then we are left with the maintenance, our net income, which helps maintain and helps produce things, the money we have left to do things with. So again, look at that posted drawing, and that should help you with that. So the whole bar is our gross income. The maintenance, egg, and tissue is our net pay, our take-home pay. And then the urine, the feces, the heat increment are the taxes that are taken out in some way, shape, or form. So you've got that whole reference here. If you want to print it out and play with it, this is from the Scientific Farm Animal Production, 8th edition. So we're going to switch gears a little bit, talking about how do we quantify this energy. So the first question we have to ask is, what is a calorie? The real question we have is, what's the difference between a calorie, which is a small c, and a calorie, capital C? So what is a calorie, small c? It's the amount of heat that increases 1 gram of water 1 degrees Celsius or centigrade. If we capitalize that C, the calorie now is the amount of heat to increase 1,000 grams of water 1 degree C. So 1,000 grams is a kilogram. 1,000 grams of water at room temperature is equal to a liter of water. So you get an idea of what we're dealing with here. So when you look on a cereal box or anything that has nutrient information, the calories there you see are really kilocalories. They don't capitalize and lower case the C the way they should, but that calorie in a slang term is actually a kilocalorie. So we're looking at feed calories. This is small c calories. If we look at a gram of each of the nutrients, the carbohydrate, the protein, and the fat, we have gross energy there versus metabolizable energy. So carbohydrates, we have the same gross energy, pretty much perfect in the small intestine. If we put a gram of carbohydrate there, pretty much all the calories will be absorbed. Nothing's going to be lost as methane or urea. So 4 is 4 calories per gram. If we look at our protein, as we use them to burn for calories, we're going to have 5 gross calories per gram. But because we have ammonia associated with those molecules, and we can't get that, it gets put in urea, we're only going to have 4 metabolizable calories if we use it for burn the protein for energy. So we're going to lose a calorie there per gram. If we look at our fats, we note that on a per gram basis, they are more calorically dense than the other two. Specifically, if we look at the ME, we have 9 versus 4. So this is where that TDN, this is where that 2.25 times comes from. A lot of people think that, well, it's all fat, it's going to be multiple times. It's only really 2.25 times. So if I eat twice as much carbohydrate, I've got the same or 2.25 times the carbohydrate, I'm going to have the same caloric intake and I'm going to get just as fat. So this overemphasis on fat-free diets has actually probably been to our detriment because we don't understand that 2.25 relationship. If we look at our hierarchy here, calorie versus kilocalorie versus megacalorie. So if we talk about the grams of water that can be increased 1 degree C, a calorie will only do 1. A kilocalorie will do 1,000, or a kilogram, or a liter of water. A megacalorie is going to do 1,000 times that as we move forward. If we think about the megacalories needed when we balance rations for our cows, we use megacalories. So a weaned calf gonna go anywhere from 2 to 5, depending on how fast they're growing, what environment they're in. If they're in a colder environment, they're gonna need more calories. Breeding age heifer, anywhere from 10 to 12 to cover all of her needs for energy. A lactating dairy cow, you're probably going to have at least 20. You may have 50 plus megacalories per day. So if we look at this, our weaned calf is about what we are in weight. So a megacalorie is going to be 2,000, equal to 2,000 of our calories. So we as humans need about 2 megacalories per day to get through the day. We're about the same size as a calf, so we have the same energy requirements there. So megacalories, what we need per day, what's consumed, dry matter intake times the concentration will give us the megacalories per day. And again, it's about the nutrients consumed. It's not about the concentration of the diet. It's about the total megacalories consumed. So we want to focus on that. So we're thinking about our dairy cattle. We've got carbohydrates. So one of the main reasons we have carbohydrates is to provide energy to the body. Most of what we get our energy from is carbohydrates. That energy is going to provide for our dairy cattle energy to the microbes so they can grow and live happily. It's also going to provide calories to the animal. The other purpose we talked about with carbohydrates is to build things. We take those carbohydrates, we use those carbon skeletons, those pieces of those molecules, to build the components of a body. So molecules, organelles, cells, tissues, bodies. Again, build or burn. We've discussed that before. Our last slide of the day, we're going to talk about megacalorie intake. So if we look at our axes first, we have the level of energy in the diet. So if we start with a high NDF, low NSC diet, the caloric concentration per pound is going to be a lot lower than if we take the high NDF or low NDF, high NSC diet. So we can assume that the non-structural carbohydrates are more or less 100% available. The NDF is somewhere 50, 60% available to a cow. So the more of the 100% we have, the higher the energy concentration in the diet. And we have to think about energy intake. What we're looking for is this plateau area between the two circles to maximize our energy intake. If we've got a lot of NDF in the body going up the slope here on the curve, we're going to have an area where fill is limiting. As we said with NDF, that's an indicator of how much the cow can consume. Those apartment building thing, the volume of feed is very much related to the NDF in the feed. So going up that slope, as we get to the top of the curve, it's limited by NDF, and we'll call that fill limitation. They can only eat so much NDF a day. There may be a desire for more calorie intake, but they're limited by the amount of NDF they can consume. We want to have this level stop here, and then we start to get into trouble when we have diets that are too low in NDF for our cows and too high in non-structural carbohydrates. We start to get acidosis in the rumen, and that's going to lead to the cows not feeling good, the fermentation not working right, the extraction of energy is going to be depressed. So we're going to have damage, so the overall energy intake will be reduced. So we could call that energy limiting intake.